And welcome back to my Electronics Experimenters Kit series of videos. In experiment 17 we'll be looking at the common component faults that can be found around the circuit and what effect they have on the circuit, how they affect the DC conditions and the input and output audio. Right, so let's go and have a look at the common emitter amplifier with faults. This video is sponsored by PCBWay. Whether it's standard PCBs you want or advanced PCBs, or for that small, confined and well packed piece of kit, a flexi rigid to save on the wiring and the PCBs. They'll also do assembly, and if you don't want to do the assembly yourself, then you can order a stencil to do the surface mount yourself. And of course, once you got your board finished, you might want a box to put it in. And so they do CNC machining, sheet metal fabrication, 3D printing, or if you're going to sell a few, you might want to look at the injection moulding and vacuum casting. So the next time you're doing something, don't forget, pop over to PCBWay and see what they can do for you. Well, I thought I'd drop a different type of video on the common emitter amplifier, showing a few component faults and how they affect the operation of the amplifier, just to show what a simple fault can do and maybe make some fault finding a little bit easier. So I'll start with faults from A to H, just showing the DC conditions and what the input and output signals looks like. And once we've looked at all the fault conditions, we will then in the final section work out what the fault is. I will leave a timestamp at the end of the fault so that you can, if you want, jump forward to where the answer is. But my idea was not to put the answer straight after the fault, to give you a bit of time to think about what the fault could be, basically. But either way, I could be wrong 50% of the time. People might have wanted fault answer, but you've got to do it one way, and this is the way I chose. So let's get on with the show. Right, this is the first fault, and what we shall do, we shall look at the base voltage, because as you can see we have an input signal but no output signal. And what have we got? We've got about, according to the meter, minus 1.24 on there. It's a minus figure. You don't, if you get minus in figures, it means there's probably main sum. The DVM is rectifying it, because the circuit can't produce a negative voltage. It cannot produce something less than 0 volts, because that's the lowest value coming out the power supply. But what it can do, because there are diodes in the transistor, any noise being picked up by the circuit can be rectified by those diodes, and you can get negative voltages floating around. If I put my finger on there, it will probably get worse. But if I ground my finger, yeah, it just changes. Everything changes. It's just voltages floating around. If I pull it up like that, you know, I can pull it positive. It's just floating around. That might give a bit of game away then, where the fault was. Right, so let's have a look at the collector voltage. And here we have the collector voltage, 8.98 volt. We'll change them on the thing so that you can look at that after I move it. And then I'll move it to the last voltage down here. And again, we've got a silly minus, one of those silly minusy voltages, which is just noise being rectified by the meter. So minus 1.29 millivolts. And who noticed the mistake up here? Of course, I can get that in the right place. That should have read millivolts. There's the voltage conditions, floating around doing nothing, floating around going nowhere, 8.98. And if I stick it on the supply, which is about 9 volts, yeah, it's 8.98. So that's basically hit the supply. So we now have fault B. So let's do our voltage checks. What have we got on the base? So we'll change that on there, 2.32. So what's on the collector? What's on the emitter? 1.63. So we can see over there the base is pulled quite high, 1.63 to 2.32. 2.32 minus 1.63. 0.63, nearly 0.7 of a volt, 0.69 of a volt, which means that transistor is heavily turned on and fully saturated. And to give you the clue that it's fully saturated, look at the voltage drop across it. 0.05 of a volt, 50 millivolts volt drop across that transistor. That transistor is fully saturated, and so it's also affected the input signal. Look up there, it's dropped it a bit because the impedance around this area has dropped, and it's affecting the signal generator. But what could be causing that? Why has the base gone so high? Right, we'll move on to fault C, or number 3 if you're into numerics. And what we got here, the input is present, there's no output. So again, let's measure the voltages. So, the base, what have we on the base? 693 millivolt. What about the collector? 64 millivolts. What about emitter? 58 millivolts. So there we have it. Quickly move along to fault D. Again, we have an input signal, we have no output signal. So again, we'll repeat our voltage measurements on the circuit. So we have 1.55 volts on the base. We have 8.98 volt on the emitter. And we have 1.17, about 1.6 volts on the emitter. Again, we have a diode through here. So we're probably seeing that voltage by the fact that I'm giving current somewhere to go. So by putting my thing on here, I'm enticing current to flow through the diode into my meter. Yes, it's just floating around. So it's not, now we're into the millivolts. Let's go back to this side. Yeah, it's just kind of floating around. Not to be trusted. That voltage shouldn't be floating around. Fault E. We're still on the external components, so it's fault E. Right, we can see we have an input. We do have an output. But let's check the voltages. Right, 1.488. What about the collector? 5.07. The emitter, 838. What does that tell us? We've got the right bias voltage for the base. We have the collector sitting where we want it. We have the DC conditions on the emitter resistor exactly how we want it. And we have output. You can see how noisy this scope is and why having it on averaging helps. But we are now down to 50 millivolts peak to peak. Or no, sorry, 50 millivolts per division on the bottom one. So it's not just the fact that we have, let's move the true up a bit, maybe that'll help. Oh, no, look, it's completely bollocks. Don't you just love a scope like this? Absolutely shite. It's never worked very well. You know, at points you can get it to trigger and you change the chime base and you go down a couple of steps on the time base and it will just refuse to trigger again. it's just so inconsistently bad. Oh well, less of that rant. So what's happened here? Why have we got DC conditions are okay, but the gain has dropped quite a bit? Right, now we look at fault F. So let's measure some of the voltages. So the voltage on the base, amend that so we can see it for more time. 2.099 volts. Voltage on the collector, and the voltage on, so I'm not sure how well it's showing up down here. Maybe I'll make that a bit bigger. But as you can see, the input is noisy, but kind of you can't see it as sine wave. So we're seeing some issues around here. But what do the voltages tell you? Voltage on the collector is 2.099. The voltage on the base is 2.099. They're identical. Now, why would they be identical? There is current flowing, because if there was no current flowing, that would be closer to 9 volts. And it does show there's voltage, there is current flowing, because we got 1.43 volts across the emitter resistor, which is R4. So we have a problem. Now, what would be causing something like that? What would you expect to cause the same voltage on the collector as on the base? Right, here we are. Well, fault G. What have we got? We have a mucked up input. Input signal is very low. We have no output. So again, let's have a look at the voltages, and I'll adjust the voltages on the drawing so that you can see what's going along. Right, what have we got here? We have 99 millivolts on the base. We have 8.97 volts on the collector. And we have 99.22 millivolts on the emitter. Right, this is going to be the last fault of the day, fault H. And right, let's get in and measure the base. We'd always start with the voltages. So measure the base voltage. Come on, stay on. There we go. Oops, fallen off. Something's pulling on the lead, that's better. Change the voltage in the drawing so we can have reference for it. And on here we have, it's fallen off, come on. These aren't the best of clips, expensive, but not the best. Right, and on here 1.577, close enough. And on the emitter again we have 1.57. Right, that's the end of the fault section, and we can move on to the answers section. And you know, I hope you find the answers interesting, and I hope this video is not too long and too boring. So here we go, eyes down for the answers. Right, this is a simple fault. There is a simple fault because we should be expecting 0.6 of a volt across, or 0.7 of a volt base to emitter. And what are we getting down there? Virtually nothing. So that point there and that point there are basically at ground, which means for that to be at ground, no current flowing. For this side to be high, no current flowing. So why is there no current flowing? Well, there's no current flowing down here. R1 is open circuit, so the base is being pulled down by I2, no base current. Transistor is fully off, therefore no current. No current flowing, can't be any output. Simple as that. And to prove it, I'll just put this link back where it should be, and it's all hunky-dory. We're back to where we should be, and we're back to a reasonable 0.48 on the base. And if I put this, I suppose I'm not going to do that. I could reference it, and or we could just look down here again. It's going to be about 0.8 of a volt, about 600 millivolts difference. So that was fault A. Well, again, this is a R1, R2 problem. It's a biasing issue. So what happens that normally, the current flowing down here, there's enough current flowing down here and some current flowing through into the base so that you bias the transistor correctly. So what's happened? Well, we've lost R2. R2 is no longer there. So all the current that's flowing down here is trying to go through the base. Now the base current is going to be limited by the current gain. So that's the limiting factor. The current, the HFE, or the current gain of this transistor, is the limiting factor. And so it's got into fully saturation. The output will be heavily distorted. So we can see here the output has gone. If you drive a harder signal in, you might affect the base biasing conditions. So you might get a bit of a signal out
but the negative part of the signal is going to be heavily clipped. And just again to show that it is in fact the bottom resistor, I'll put this link back where it should be and give it time. It will all come back to normal. The reason the scope is so slow is my Handtech scope is so bad that the input I've had to put on averaging, and it's quite a high averaging value, so it takes a while to settle down. Otherwise the input signal you can't see, it's just complete noise. So Keysight, if you're watching, could do a new scope, or anyone who does these decent modern scopes. I'll do a review for you. We have about 600 millivolts base emitter, so this transistor is kind of biasing itself, but we have no current, no voltage drop across the resistor, the emitter resistor. It's at 470 ohms, so that means there's no current flowing down here. At this point here, which is the collector, again 64 millivolts. You know, there's no current. Why is there no current? Well, there's no current because there must be a problem with R3, because we know that if R3 was correct, that would be around 5 volts. So the fact that there is no current down here points to one of two things. It's either a problem up here or a problem down here. Now if we got some current flowing through the base, it must be flowing down here. Something is holding that 0.6 volts above that, so there must be current flow down here. So that would point to the fact that the collector resistor R3 must be open circuit. And if I put it back to where it should be, everything will come back to normal. And why is this voltage close to the supply rail? Now if it's close to the supply rail, then there can't be any current flowing through here. No current flowing through here means there is no current flowing through here. So this point must be open circuit, which is probably why when you connect to it you get different values. The meter's not behaving if I put my finger across it. You know, again, we can do things with it. It's showing you that this point here is not tied to that point, the ground, in any way, hinting that R4 is open circuit. So again, if I pull it out, put it back in properly, and everything is now hunky-dory. We'll be back to the 0.8. Doesn't want to stay on. Come on. It just doesn't want to stay on this time. There you go. We're back to the sort of 800 millivolts that it's designed to be at. So, next fault. We got DC conditions are okay, but the gain has dropped quite a bit. And that's because we've introduced a sort of negative feedback. As the current is changing in here, the voltage across the resistor is changing. That's altering the base drive, and we are getting some differences. Also, the gain is RC divided by RE. Now we have little RE, which is the intrinsic sort of value of emitter resistor, and we have RE R1, the 470. So you've got to add those two together, calculate the gain with the collector resistor, and that will give you the gain. What's happened here is the capacitor has died. So the capacitor is now open circuit. So that resistor is playing part of the gain circuit. Now if we put the capacitor back where it should be, so now the AC is bypassing that resistor. So that was basically all the faults surrounding the components. I won't bother doing these ones. You know, if they die, then you're going to put DC. You might put a DC condition on here, and it will drag it down. If it goes open circuit, there's no signal. Open circuit, no signal. If it's short circuit, then whatever happens here is totally dependent on what the DC conditions are on this side. So it's kind of, you know, that DC voltage will just get dragged somewhere
But then you just measure across the capacitor, and if it's the same on both sides, there's probably, or DC wise, if it's exactly the same both sides, you've got a short. What would be causing something like that? What would you expect to cause the same voltage on the collector as on the base? Well, in my eyes, the only way that's going to happen, because at worst case it should be a diode junction, the only way that's going to happen is if there's a short. So if there's a base collector short, then we would expect to see the same voltage on the base as on the collector, which is exactly what we're seeing here. And if I turn the power off and pull this out, turn it over, and there you will see we have a base collector short. If I remove that, put it back in, put power back on, and there we go. A reasonably happy amplifier, even though the trace is rubbish on my scope. I don't think you can actually see it up very easily, but if you look there, that's where it thinks the 0 volt is on an AC coupled scope. You know, it should be down here in the middle like it is here. You can just see the 0 volt marking there, so that's should be swinging either side of that. But here you can see it's completely rubbish, and it's on AC, so it should be swinging either side of that, but it don't. So I wouldn't buy one of these scopes again, even if they offered it for free. Right, so that's that fault. Right, here we are, fault G. What have we got? We have a mucked up input signal is very low. We have no output. So again, let's have a look at the voltages, and I'll adjust the voltages on the drawing so that you can see what's going along. Right, what have we got here? We have 99 millivolts on the base. We have 8.97 volts on the collector, and we have 99.22 millivolts on the emitter. So what is that telling us? Well, that's telling us there isn't, well, that one there is showing that that voltage there is virtually the same as the voltage up there. I think my power supply is running at about 8.97. I'll stick up there so you can have a look. 8.98. So it is virtually the same as the collector. So we have no current flowing down here. And why don't we have any current flowing down here? Well, 99.22 millivolts and 99 millivolts here. There's no difference between the base and the emitter. Now we would expect to see a forward bias diode there, so we would expect to see, if it was happy, 0.6 of a volt thereabouts. And of course no current flowing, so we have no signal on the output. And so what would you guess would be that fault? Well, let's turn power off and we'll pull this out and we'll have a look. And what have we got? We have a short between the base and the emitter. Again, if I put that back out and put it back in, the circuit would work fine. So, what does it tell us by looking at these voltages? We have 1.55 on the base, which is not too far away from where you would expect it to be. But we also have 1.577 on the collector, and we have 1.57 on the emitter, and we have no output. Now, the fact that we have a voltage here that's not the rail, supply rail voltage, means R3 is dropping a voltage, so current must be flowing down here. The fact that 1.57 and 1.57 are the same, that kind of hints that there is a fault in the transistor, because they should never, emitter and the collector in a circuit like this should never be the same. And of course we've got the base, which is a bit higher than what we expect it to be. But I think the big game changer is, of course, that voltage and that voltage are the same. So the current is flowing straight down there. And if you do the voltage divider calculations, you'll find that 2K2 and 4K7 and 9 volts, the center point will be 1.57, because effectively that transistor is out of circuit. There is just a connection directly from here. That transistor has gone collector emitter short, and therefore no output because there is no gain. It's just a voltage divider. And because there's still a diode connection across here, we don't see a very low impedance here, and so the input level is roughly what we'd expect. So, and just to show you the actual fault, I'll pull out the transistor, and there it is. We have a wire link between collector and the emitter. And just for a last ditch go, or last effort, we'll stick it back in the circuit, power back on, and there's our happy circuit on a crappy scope. So, well, I hope you learned something from that, found it interesting, and if you did, hit the subscribe button, click on the like button, and please comment, and I'll catch you on the next one.